I did not. Guys, there's a tutor center upstairs. Do y'all use the tutor center? Any feedback on the tutor center?
Not really anyone in there.
Go ahead.
Not really anybody in there.
I do, and every time I go, there's nobody available for OChem.
Nobody available?
I tried all hours, and no one is available every time I go.
Well, there's open help in the academic success center, and like he's pretty good at teaching. So like that's a good source.
What's his name?
It's like Eric.
Is that the last one?
Just like what's that Eric?
Any feedback on the tutor center up here, please let me know. Dying chemistry. I know y'all have been dying to get back to that handout. Terpenes, right? Okay, guys. Please remember the seminar Friday at 1 o'clock. Room over there, the tutor room 1002.
It's going to be explosive, right?
Explosives, yes. Dr. Sabatini works for the U.S. Army, does research on organic chemistry, developing new explosive compounds, synthesizing explosives. Got to be very careful when you synthesize those things. Trying to recrystallize, you don't want it to explode on you. Okay, dying chemistry. Reacting with something like HBr, electrophilic addition reactions, carbocation intermediate. Here we can have two outcomes, 1,2 addition, 1,4 addition. The 1,4 addition comes from the fact that the cation is going to be resonance stabilized. Okay? And through resonance, it's almost like a rearrangement of the cation, but it's not, because it's the same cation. But the cation just has two different sort of forms. That's also wrong. It's only one cation, so we got to kind of get a handle on that. But take-home statement. Whenever you do these, we're doing conjugated dienes. Everybody saw that word up there, right? Because every word in the heading is important, or I wouldn't have put it there. Conjugated dienes. Whenever you're doing conjugated dienes like this, two-enes, dienes, I didn't say tetraenes, dienes, you always want to form resonance stabilized allylic carbocation. Here it's kind of intuitive. Where we're going to make cation. First off, this is a symmetrical diene. No matter which one you work with, it's going to lead to the same thing. Next page you won't have non-symmetrical. We'll have to decide which alkene. It doesn't matter. Over here, cation on left or right? Where are we going to make cation?
Right.
On the right, and you could have answered that a month ago. But more importantly today, on the right, because on the right, new H here, cation on the right, because it's allylic. Underline. Since it's allylic, not only is it secondary compared to over here been primary, but more importantly now we can also do resonance of the allylic cation. And so you get resonance structure always make allylic cation. So you're always going to make cations either here or here. Never on the outside. Okay? This cation has two different sort of major contributors. One major, one minor. But this is how you get the two different products. Br can attack here, that'd be 1,2 addition. Br can attack here, that's 1,4 addition. But that's only one intermediate here. Okay, we looked at reaction coordinate diagrams. Any questions about why you get 1,2 versus 1,4? Here's a summary. Take this reactant with low temp. Which product is formed first? Fastest. 1,2, correct? Fastest means it's going to form first. Fastest runner will get to the finish line first. That's called the kinetic product. With heat, though, we can actually go all the way and end up getting the thermo product. But that's because this thing, which is formed first, can convert to that thing. How would it get to that thing? It would have to go backwards. Okay, the mechanism is here to get here, but then you go over there, it's got to go backwards. Going backwards involves the BR turning around and leaving. Okay? That's just the BR leaving, nothing kicking it off. We will do that down the road more. Once it leaves, what do you get? You get this cation back. And it's shown here. Well, then the BR that left can turn around and add to the N carbon. And that gives that. Well, guess what? That can leave, and you go back here, and it can add here. At this point, you have an equilibrium back and forth. At that point, thermodynamics takes over, which is going to be favored if thermodynamics takes over. The more stable alkene, which is this one. So if you can give some heat and let equilibrium take over, that'll become your major product. So it's reversible with heat. Br as a leaving group. Let's see how we did over here. Which product at the top? Anybody get a product here?
Third one?
Third one? Third one? Cold temp, what product we're going to get?
1, 2.
1, 2. Cold is always 1, 2. What if this was heat?
1, 4.
You've got to be careful with heat. Heat could actually be either. In the example, it was 1, 4. Some books will tell you it's always 1, 4. That's because they don't want to do anything else. How do you determine which product is going to be favored with heat?
More resonance.
Which establishes the equilibrium? Which one's favored? The most stable one. That's always the case. What I'm telling you is the 1, 4 is not always the most stable. Sometimes the 1, 2 may be the most stable. Can you look at two different alkenes and tell which is most stable? I hope so. We did that a month ago and it was on the test, probably, etc. We've looked at how to determine alkenes are more stable. Okay, cold temp, 1, 2. But here though, this alkyne is not symmetrical. It's not. That's nothing. Where are we going to make cation? Where are we going to make cation? Second sentence back over here. But you must determine which allylic carbocation is best. Here, both allylic carbocations would be the same. If I reacted here, I would get cation there. If I reacted here, I would get cation there. That's the same structure, just flipped around. So, like I said, it doesn't matter. But in the one we're looking at, it does matter. So we got that methyl group. Question is, where do you want to make cation? Where's the cation going to form? Okay, let's react here and let's see. If that reacts, if this alkene reacts, are we going to make cation on left or right? On the right, correct? Because it would be allylic. It would also be secondary, so But what if there was a methyl here? Which side would you make it on, left or right? No, it does matter. It would still be on the right because you would want to make an allylic cation. Allylic cation. Resonance stabilized would be better than not. Please understand that. Boom, 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 boom. Methyl here. Okay, I'm going to do this systematically. Okay, we're going to look at it. That would give that cation resonance structure because this is allylic, meaning it's conjugated with the remaining alkene. That gives boom, 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 boom here, new H here, and cation on the end. Right so far? Let's assess these. Two fake structures. We know their true structures are hybrid. But it's very much easier often to assess the fake structures. This fake structure, we have a secondary cation. This fake structure, we have a primary cation. The hybrid is going to be a blend of a secondary and primary cation. I'll call that A, and this is coming to A. Now, let's look if we reacted the other alkene. All right, forget about what we've done. Where are we going to make cation, right or left? Correct, left. This is going to be B. All right, and I'll come over here, going this way. Boom, 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 boom. Methyl. New H on the end and cation there. Allylic cation. Resonance stabilized. Show resonance structure. Windshield wiper over. Boom, 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 boom. Windshield wiper over. Double bond now there. Right? Everybody windshield wiper. Boom. Double bond now here. Cation here. New H there if you want to keep drawing that in. There you go. Can we do any other resonance? No. Pathway B gives this intermediate, which has tertiary and primary characteristics, because the hybrid has tertiary primary characteristics. Which hybrid is more stable? Tertiary primary or secondary primary? There you go. This hybrid, if we drew it, is going to be better. Because of that, forget about A. We're working this way. Now the decision becomes, where is the chloride going to add? Because that Cl minus is floating around. Is it going to add to the cation here or there?
Tertiary.
1, 2, correct? What would be 1, 2? There's the H. If that's 1, here's 2. Chlorine is here. Which product is that?
First.
Now this is a next reaction arrow. That's a resonance arrow. Basically, this comes in here, and there you go. That's the product. 1, 2. That's your 1, 2 product. The new H is on the end. 1, 2. Correct. What if this reaction was done with heat? Which product would you get up there?
Same.
Why do you say same one?
Sometimes you get the 1, 2 product that doesn't mean it's more stable.
The other possible product is for the chlorine to add here.
Mm-hmm.
But isn't it all the way on the right because it's dropping that H off at the hydrogen?
What do you mean? This product already on the right?
No, you see, we've added the hydrogen over on the right, so isn't that where the chloride would be coming from? All the way on that side of the molecule?
Sure, it would have to go cross country.
Yeah.
All I'm saying though is, that's one product. The other possible product is for the chlorine to add here.
Oh, yeah.
And that would be the 1,4 product. 1, 2, 3, 4. 1,4 product. Well, which product is that?
B.
Which one?
The second one.
Okay, so this is your 1,2 product. This is your 1,4 product. Well, what are those other two? Those two are actually the 1,2 and 1,4 products coming from this initial. But guess what? We got rid of those. Because which one that I just marked out is a 1,2 product coming from this pathway?
C, the third one.
The third one is a 1,2 product coming from this pathway, and the fourth one is a 1,4 product coming from this pathway, but we got rid of those. Okay, here are your two products coming from the right pathway. Cold temperature gives 1,2. My original question was, if we did heat, which one would be formed? With heat, which one of these would be formed? This one, right? Right?
Mm-hmm.
Which one's formed with heat? In any reaction, which one's formed with heat?
1,4
1,
product.
4.
No.
Both of them.
No, sometimes it can be 1, 2. Which one's always formed with heat?
Stable.
The most stable. Which one is most stable? The monosubstituted alkene or the tri-substituted alkene?
Try.
Most stable. That's the one and it is the 1,4 product. So, yeah, it is the 1,4 product. But I guarantee you we're going to see a 1,2 product being most stable at some point. It doesn't matter, as long as everybody can determine which is most stable of two alkenes, and we did that a month ago. Okay, there's others to do. Any questions about what I went through there? I would probably remember the take-home message, including the second sentence. That's what we started with right there. See how you do on the rest of those? You can do those on your own. We may do like maybe the first one in class tomorrow. Largely with dienes, we're pretty much just going to be reacting with like HX, HBr, HCl. That's the most common. You could see some other types of reactions in some type of maybe mechanism question. The general chemistry of the dienes we cover with all that right there. Any questions about lab this week?
Are we meeting downstairs?
Probably should, yes. Downstairs. Okay, another reaction of dienes is the Diels-Alder reaction. Is this our first name reaction, where the reaction has the name of the scientist, the chemist that developed it? I think it may be. You'll see a number of name reactions, especially in Organic 2. We'll see at least one or two more here probably, like the Williamson ether synthesis, Fischer esterification. You know the Fischer projections, but you also have the Fischer esterification. Okay, there's several. And usually if the reaction has a name associated with it, it tends to mean it's kind of important. Diels-Alder, two names. Dills and alder, kind of like, you ever heard of Laurel and Hardy? We got a museum out there in somewhere. Where is it? Yeah, big metropolitan museum. This is Dills and alder. They came up with a reaction. They won Nobel Prize in 1950. It involves a diene. Classical diene reaction. Very useful. Some of this I may have taken like from the web. Okay, we'll start here. Line reaction. Is that a plus sign? I don't know what. We have this plus this. Typically, you have a diene and an ene, an alkene, a monoene. And what we can make here is a 6-membered ring with at least one pi bond. So a cyclohexene. Now we may see more than one pi bond. It may have 2, but it will at least be at least one ene there. So it's at least a cyclohexene. And let's do a little math. Because math is important here. This is 4 carbons. And this is 2. Good, good. And 4 plus 2 equals 6. Yes. We're making a 6-membered ring from the 4 and the 2 coming together. Okay. This is often called a 4 plus 2 cycloaddition reaction. Cycloaddition reaction. Oh, there it is, a little bit lower down, handwritten. Yeah. Cycloaddition. We'll use this terminology a little bit more. And more broadly speaking, it's a type of pericyclic reaction. Now, some textbooks will include a chapter near the back on pericyclic reactions. Cycloaddition is one type of pericyclic. Pericyclic reactions are, all these reactions have a cyclic transition state. And cycloaddition is one example. What does cycloaddition mean? It's cyclizing, it's making a ring, and things are adding together. We knew that because when you use a plus sign, things are adding together, right? Learned that method? Okay. So that's your terminology. Mechanism. Well, here are your mechanism arrows. Okay. First off, it's all hydrocarbon here. Introductory level, it tends to be just hydrocarbon. In advanced reactions, we can start having oxygens and nitrogens in here. So we really don't have any polarity to sort of guide us with moving in. We kind of look at this pi bond, okay, can windshield wiper out and go bond over there. Okay? But we're not doing resonance. This one can windshield wiper out and come bond down here. Well, something's got to leave here. So these get pushed up in here. And this becomes your long double bond. Where when this windshield wipers out, that's just a single bond connected there. And so the pi electrons turn into sigma electrons as this takes place. All right? Now, in terms of a little bit more theory of the mechanism, it's sort of akin to resonance. But it's not. We're making a new compound. So we're doing a reaction here. We're also making sigma bonds. And if you were doing resonance, you would not be doing any sigma bond. But really, it's overlap of p orbitals. Let's look at the two reactants. Don't we have p orbitals of the diene like this? One electron makes pi bond. I reckon we'll draw it in. One electron makes pi bond. Here's your diene. And then you have your alkene. By the way, this is called diene. The alkene is called, how do you know that? You read it? Oh, good. Okay. Yes. This guy likes the diene. We can call it a dienophile. What if this guy liked wine? Winophile? Okay. It's called, the alkene is called a dienophile. So the dienophile is also a pi bond, right? One electron, hey, there's an electron right there. One electron, pi bond, there's your alkene. What happens is these two reactants start coming together and you start getting interaction of the p orbitals there. And you get this sort of transition state, which is hard to draw, where they're all sort of interacting. Kind of like we're just extending the conjugation, but it's two different molecules. That's probably enough of the theory. What happens is, though, that these come together and then the bonds sort of just reorganize. Instead of the electrons being here for the pi bond, they end up being here as a sigma bond. And this is a little sort of magical, mystical, it's all in the transition state, which we don't often look at. Here's our conventional arrow movement. These attack here. Something's got to leave this carbon. It can't have a fifth bond. So this moves down here. Something's got to leave this carbon, so that moves up there. There's your typical. From here, you see what type of questions you have. One of the most important things of this reaction, one of the reasons it led to the Nobel Prize, is because you're able to make carbon-carbon bonds. Okay? And historically in organic chemistry, it was always difficult to get carbons to react. Because they don't have a lone pair, there's not much reactivity there. So this led to a lot, and of making lots of different rings, which before this were like, there was no way to make them. So that's why this was kind of so important. Especially if you look at rings like in cholesterol, a lot of natural products have these sort of hydrocarbon rings. Okay, examples of your dienes. Well, this is the most simplest diene, most simple diene. Important about the dienes, though, it needs to be in the S-cis form when it reacts in the mechanism. What does S-cis means? The S refers to the single bond. Okay? If you focus in on the single bond, it's sort of the terminology, the double bonds are sort of cis on that single bond. As opposed to over here, the double bonds are sort of trans on the single bond. Now these can freely rotate, so it's not like it's two different compounds. They're just different sort of conformers. But the conformers sort of go by these names. Because, again, when the diene reacts, hopefully it makes sense that the two double bonds need to be facing sort of that way if they're going to join up over here, right? So that's important to know, and that terminology there. Now our dienes can be symmetrical, but they may not be. Here we got a methyl here, but not here, so that's an asymmetric diene. Your dienes can also already be in a ring, like this here, but it's just connected in a ring. That too. By the way, this reminds me that whenever you see dienes, they're not always going to be drawn sort of like this. I mean, they could be drawn like this, right? This is a diene, it's just drawn up, and it's connected in a ring by one carbon. These guys are actually more reactive in Diels-Alder than these. The reason being because they're stuck in the good conformation. Okay? This guy cannot rotate. This double bond, this cannot rotate and have this double bond that way. Right? Hopefully you see that. Where this guy can. Because the single bond here can just, all right? So these are particularly good dienes for Diels-Alder reactions. The dienophile. How many carbons does the dienophile supply? 2? Yes. Okay, supplies to 2. And typically an alkene, all right, you can circle all your alkenes, all these are alkenes, but we can have substituents on our alkene. The most common type of substituent is a electron withdrawing group, all right, like a carbonyl. It's electron withdrawing because the oxygen is pulling away. The electron withdrawing group makes these more reactive in Diels-Alder. We'll mention a little bit why in a little bit later. Those will be common dienophiles. Okay, let's look at some outcomes. We have 2 things to look at, stereochemistry, and then we'll look at regiochemistry. Due to the concerted nature of the mechanism, what do I mean concerted? When we did the mechanism, was there any intermediate in this mechanism? No. You had the 2 starting materials, and you had the product. What was the only thing in between? It was called the electrons?
Movement.
Yeah, what's the general, what was that though? I think I said, I mean, if you have a one-step reaction, what's the only thing that's in between? It was on the thermodynamic handout from a month ago. The transition state. Okay? All we have in the Diels-Alder is a transition state. So basically it's one step. Now typically concerted means that multiple steps are happening at the same time. It's really only one step. So is it really concerted? It's hard to say. The important thing is there's no intermediate where you can maybe have some free rotation. In the end, the stereochemistry of the product comes from the stereochemistry of the starting materials because nothing has a chance to rotate due to the concerted nature. For example, if you take this diene and this dienophile, 4 plus 2 is 6, yeah? Get a cyclohexene, there it is. But you got these 2 substituents. All right? They're going to be here. And by the way, some of you guys won't put the substituents here. For some reason, you'll put them here and here. So you got to recognize where your substituents are, etc. Okay, but those are going to be cis because now in the ring we know that these are tetrahedral. And these can be cis or trans. They're going to be cis. Why? Because they were cis here. They're cis here about the double bond. They're cis here on the ring. Now, I'm not going to go deep into this and do like transition states and show you why it maintains cis. I'm pretty much just telling you this here. Things don't have a chance to rotate. Now, if this was an advanced organic chemistry, we might do modeling of this transition state and really prove why cis becomes cis. I'm just saying it as sort of making statements here at the introductory level. On the other hand, and seeing options, alternatives, we could react this with this, 4 plus 2, but this would give trans on the ring. Why?
Those trees.
because they're trans there. Okay, stereochemistry is maintained. So, is Diels-Alder a stereoselective reaction?
Yes.
Yes. You do this, you're only going to get trans. Do you get any cis here? No cis. No trans. Diels-Alder is stereoselective. Well, perhaps you're saying that's kind of a vague term. Because under stereo we have two. What's the relationship between cis and trans? Diastereomers. This reaction is diastereoselective. Right? Is it an antioselective? Plus an antimer. It's diastereoselective. Not an antioselective. So we still have never done a reaction that's an antioselective, right? Now you can make Diels-Alder an antioselective by doing something to it. And there may be an example in the warm-up page on the next handout. The one I think I asked you to print on your own. Everybody got that one today?
Yes.
We'll probably definitely be looking at it on Friday. All right. What about stereochemistry in the diene? They can have stereochemistry. Look at this. Both of these double bonds here are E. That is trans. Product here, 4 plus 2. By the way, this is a triple bond. This is going to give a pi bond over here. How do you zip this together? This attacks here, this attacks here, this comes down. When this comes down, we're putting a pi bond here. Why is there also a pi bond over there? Because only one of them moved up to make single bond. We're left with a pi bond. What we can say here is that your dienophile can be an alkene, but it can also be an alkyne. Cyclohexene, it's in there, the cyclohexene. We just have another double bond as well. Okay, what type of stereochemistry does this have? Any stereochemistry here? No, they're planar. There's no projections there. Planar on the alkene. Of course, these groups have to be that way because you can't have a ring this way. Okay. The only stereochemistry here is here and here. Well, these can be cis or trans. What are they going to be? They're the same here, so they're going to be the same there. Now this is where we would really maybe look at the transition state and see why this makes this. But I'm not going to do that here. I'm just saying it is consistent. Same here, same there. And then, for example, if we look below, what's the difference in these two? That's E.
Z.
This double bond is in the Z configuration, though. Cis. Notice that, right? So these are opposite. It's the same reaction otherwise, and so we get opposite, or trans. So again, we get that maintained, and hopefully you're maybe wondering, why is it maintained? Because it's, hopefully you just you don't like these statements. I would wish that we could spend a week looking at transition states and modeling and etc. That's a little bit beyond the scope. Consistencies though, yeah? due to the concerted nature. That page came from the web. The next page was sort of my repeat, but it's really a repeat. Top portion is just a repeat of what we did. We can pick up here. Please provide a product for this reaction. We'll look back at it. And then there's some examples below. Okay, see how you do with some of these deals, all their examples, based on what we looked at, what's in the handout. This one here is used to make the antiviral or influenza drug, flu medication called Tamiflu. It's one of the first steps to make Tamiflu. Also in Diels-Alder is regioselectivity. What we looked at before was stereochemistry. What about regiochemistry? Four plus two. Okay. Which product's going to be formed though? What's the relationship between these two? Are they stereoisomers? No, they have different connectivity. They're regioisomers. Things have bonded in different regions. Yeah? Which regioisomer are we going to get?
Left one?
Well, we need to look at this. Somebody have an answer?
Left one? The first one?
Well, this is something where I don't think you would really have a good handle on it at all right now. Some things I would expect you to have a good handle. This, no. But someone over here said something?
Well, I said the first one.
I mean, why?
Well, just because why would the methyl and oxygen flip over the ring for no reason?
Are you saying this thing can't be drawn like that? It can be drawn like that. In fact, that's what we're going to have to look at. Which way is it going to come together? Like this, or is it going to come together with this flipped up? That's what we need to look at. Okay. This involves a little resonance. It involves some very fundamental things. And the fundamental things are just important, are actually more important than just predicting this outcome. This is a chance for us to put to use some of our fundamental things. First off, and we'll focus on this, but first let's go over here. This is going to be sort of a take-home, and you'll see this more in organic too. All right? What we're really looking for is some polarization, because if we can find some positive and negative, that's what's going to come together. All right? Question, of the two carbons that react here, which one is partial positive or negative? Well, here's the answer. First off, what type of group is this? It's an electron withdrawing group. And this is going to help. We said that earlier. Let's look at some resonance here. We know we can polarize the pi bond to the oxygen. We need sort of lots of room here. We'll do this, then we'll do this, then we'll come back and do the reaction. But I'm doing resonance here. Boom, 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 boom. It's a resonance structure. Polarization of the carbonyl. This hasn't really done anything to our 2 of the 4 plus 2. Okay? What's the next resonance structure we can draw though? Can we draw a resonance structure involving this here?
Yeah.
What can we do?
Windshield wiper down.
Windshield wiper up? Give that there. Now, we could have also have done resonance structure with this lone pair and move it in. It could have been another resonance structure. I'm not going to show that because the important one is dealing with kind of these two carbons. Can we do any other resonance structure with these two carbons? You don't have to think theoretically. Just think moving your electrons with your arrows. And the answer is no. Now we can draw a hybrid. In the hybrid, which of the carbons, top or bottom, has some partial positive? The bottom one. You see it from that fake structure. Did we ever put positive on the top carbon here? No. From the carbonyl, the first carbon this way is called alpha, the second one's called beta. The beta carbon is partial plus. We see that if we understand resonance structures and polarization by the carbonyl. Some fundamental stuff there. So, I'm going to draw a partial plus right there. The beta carbon. And that's typical for your dienophile, because the withdrawing group typically makes the beta carbon partial plus. That's why the withdrawing group helps the reaction, we said earlier. That's partial plus. You can identify a partial negative over here. Those two carbons are going to end up bonded together. First off, which carbon could potentially bond to that carbon? This one? No. Only that one or this one are going to potentially bond to that partial plus. Question is, which of these is partial negative? Let's do resonance structures. Can you draw a resonance structure of that? It's a neutral molecule. Where do you want to start with in doing resonance structures? We said this. Where do we say start with?
Polarity. Polarity.
Double bond?
Not double bond. Somebody said polarity, but
A lone pair.
lone pair, right? Didn't we say that when we were doing resonance? If not, please look back where we said it. Lone pair. Great place to start with resonance. What can we do with it? Well, what if I do this and then move these out here? Boom, 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 boom. Oxygen now double bonded, one lone pair left. That's a positive charge. What's here? Lone pair, that's a negative. Okay. What can we do with the lone pair now that we're dealing with?
Make a double bond.
We can move them here and move these out there. What does that give? Boop. Boop. There you go. I think that's all the resonance you can draw with that lone pair. Okay, of the two carbons that may potentially react and bond up with that guy, which one is partial negative? Let's investigate the fake resonance structures. Which one has some negative character? You see it, right? Okay, that one. Does that carbon ever have any negative character? No. There's your answer. This carbon is partial minus. The resonance donation of the lone pair. So, in the product, that carbon needs to bond to that carbon. Because, guess what? When these are floating around, this end is going to be attracted to that end. And you're going to get that reaction. So, indeed, we need to flip this guy over. Okay? I'm going to flip it over right here, I reckon. Boom, boom, boom. Have the image like this. Flip it over. So this, now here, right? This carbon bonds here. So So we zip it together like this. And indeed, this carbon is now bonding here. When this flips over, this carbon is now bonding there. And which product does it give? Well, let's draw it and then see which. It's going to be a 6, right? Got a methoxy here. We got a ethyl ester here. Where's the double bond at? Right there, right? Goes right there. Which bonds did we just make? Here's our 4. There's our 2. We just made that bond and that bond, right? 4 plus 2. These groups are next to each other. Which one is it? It's that. All right, that's how it's going to zip together. And that's regiochemistry, because okay, these are not stereoisomers. These have totally different connectivity, right? They're constitutional isomers, but in the context of the reaction, we call them regioisomers. Now, are these cis or trans? Based on previous discussion, we don't know. Because these, if the previous discussion was either these two relative or those two relative. We have not discussed this and this relative. We don't know. I'm not going to go there, so I'm just going to leave it generic and not discuss it. But if you look at it, we did not discuss that relative stereochemistry on the previous page. See some of you in lab tomorrow afternoon. Our speaker may be attending lab.